A very good afternoon to all. Welcome to another session on remote sensing and GIS. We'll start the session in a few minutes. I hope you all are able to hear my voice. Yeah, thank you, Jashwant, for the feedback. A very good afternoon to all again. Welcome to another session on remote sensing. So, in this session, we are going to see the electromagnetic spectrum that is used for remote sensing. What are the spectral values or spectral regions that is used or that was used in remote sensing? So let us go to the concept of remote sensing first. Okay, so the concept of remote sensing is that remote sensing is defined as the science of acquiring information about the objects of interest without actually being in contact with it. So this definition is being given in every introduction class of every session, so it is the same. So how do we do remote sensing without actual touching the objects, or how do we acquire information about a particular land or a water or a object or a ship or an ocean or buildings or trees without actually touching it? Is that it is being done by a sensor or by a sensing method that records by either the principle of reflection, emission of the electromagnetic energy, and process them, analyze them, and apply to that particular information. So here we can see an example in the diagram. We have a sun, so which radiates energy. So the sun's energy, when it falls on the earth, gets partially absorbed or partially reflected. So this is a part that is generally reflected or absorbed or emitted. So that energy absorbed by the sensor is being stored, processed, analyzed, for providing that particular information. So this is what concept of remote sensing is. Okay. So the sun's energy falls on the earth, gets partially reflected, partially absorbed, partially emitted. So that reflected, we generally use it in remote sensing. So you can see the sun emitting sun's energy. So reflection, absorption, emission takes place partially. So the part that is reflected, okay, is being sensed by the sensor, by the aerial platforms, and this data which is being acquired is given for processing, analyzing, and applying that in order to observe that particular area's observation. So this is how remote sensing is working. Okay, you can see that the elements involved in the remote sensing are energy source, which is A, you can see, then which is used as illumination. Then we have the radiation and the atmosphere, which is B. You can see wherever B it is, capital B is radiation in the atmosphere. Then we have the interaction with the object. So it interacts with the object that we want to observe, or the geographical area, or the geographical point, or the location. Then recording of the energy by the sensor. So a sensor, either it's satellite or in aerial surveying or photogrammetry or aerial photography, takes interacts with the sea object, okay, with the help of a sensor. Camera is a sensor, so it takes photographs or whatever might be. By emission or reflection or absorption, it will sense the data. Then E is your transmission, reception, and processing. So that is being given to earth station. So this is your earth station. Transmitting, reception, and processing is all being done in E. So this is your E. So then it is given to a satellite and then again back to the earth station, or directly from the aerial platform it is given to the earth station, or through the satellite to the earth station. Then it is being processed. Then it is interpreted by using interpretation or analysis F. Then it is given to the corresponding application, for which purpose we are monitoring this. C is your G. So these are the elements involved in remote sensing. Okay. So what are the energy sources? You can see that energy sources or illumination. What is that? All the matter with a temperature above absolute zero, measured in Kelvin, radiates energy in the form of electromagnetic waves of various wavelengths. All matter, the temperature above absolute zero Kelvin, radiates energy in the form of electromagnetic waves of different wavelengths. So this electromagnetic radiation, or we call it as EMR, is a carrier of electromagnetic wave energy by transmitting the oscillations of electromagnetic field through space or matter. So this is what is your energy source or illumination, which is traversed, which is transmitted, reflected, or observed. Okay, electromagnetic radiation. So which is a carrier of electromagnetic energy by transmitting the oscillation of electromagnetic field through space or matter. So this EMR, or the electromagnetic radiation, has two characteristics. They are wavelength and frequency. So I think everyone are familiar with the term called frequency. One time revolutions is equal to T. The inverse of that is your frequency. And it also indicates the frequency of operation of your electromagnetic wave or electromagnetic energy source that is being transmitted. Then we have wavelength. Wavelength is this. You can see that there are three different waves being drawn. First one, second one, third one. So A sinusoidal signal from the top peak to the top peak corresponds to 1 lambda in each case, or crest to crests in a waveform. Okay. So these are the two different characteristics, wavelength and frequency, which you all are familiar right from your engineering physics, wavelength and frequency. So we'll define what is this wavelength. So wavelength is a measure in meters or some factor of meters measured in micrometers, which is represented in 10 power minus 6. So this wavelength is the length of one wave cycle, which can be measured at a distance between successive wave crests. Wavelength is the length of one wave cycle measured at a distance between successive wave crests. So that is wavelength first characteristic. Second characteristic is frequency. The frequency refers to the number of cycles of a wave passing a fixed point per unit of time. Frequency refers to the number of cycles, which is t, of a wave passing through a fixed point per unit of time. So which is measured in hertz, equivalent to 1 cycle per second, and it varies in multiples of hertz, kilohertz, megahertz, gigahertz, terahertz. So that is your frequency. So the electromagnetic energy can be modeled in two ways. One is wave motion, another one is particle motion. So this wave motion corresponds to your wave theory, and the particle motions corresponds to your quantum theory. So let us see that wave motion and particle motion, that is used in remote sensing. So all these basics you would have studied. Still we need to have a glimpse of that. Okay, so the wave motion, the electromagnetic radiation can be considered as a transverse wave with an electric field and a magnetic field. So the two fields are located at right angles to each other. So we get the equation of the shorter wavelength having higher spectral frequency, which is obtained as V is equal to C by lambda. So where V is the frequency, C is the velocity of electromagnetic energy, that is speed of the light, which is approximately 3 into 10 power 8 meter per second, and lambda is the wavelength being measured. So each electromagnetic wave represents a group of particles with the same frequency. Altogether, they have different frequencies and magnitudes also. So you can see we have an electric field E in this direction, magnetic field M in this direction. So perpendicular to both electric field and magnetic field, there is the direction of propagation of electromagnetic wave. You can see that they propagate. So the measurement from crest point, one crest point, another crest point is a wavelength, which is measured in lambda. So amplitude is measured in E. You can see that E. So with each wave, there is an electronic component. Sorry, it's an electrical component. Electrical component E and a magnetic component M. Here is the notation is like that. So the wave will propagate in this. Okay. So amplitude versus lambda. This would be your direction of wave propagation. Amplitude versus wavelength. So next is the particle motion or the quantum theory. So this quantum theory can be treated as a photon or a light quantum. So the amount of energy held by a photon of a specific wavelength is given by E is equal to h nu. So where nu is the frequency, E is the energy of a photon, h is the Planck's constant, which is equal to 6.63 into 10 power minus 34 joules per second. So the longer the wavelength involved, the lower is its energy content. So we should go for a shorter wavelength. So the gamma rays having wavelength around 10 power minus 19 are the most energetic, and radio waves are the least energetic. Okay. So it is more difficult to measure the energy emitted in longer wavelength than in shorter wavelength, just to be considered in the particle motion or quantum theory Planck's constant. So now let us see the electromagnetic spectrum. So remote sensing technology uses the visible, infrared, microwave regions of the solar radiation to collect information about various objects on the Earth's surface. So this electromagnetic spectrum has a visible region which we use to view an object with our eyes. By our naked eyes, we can view in the visible region. So this I had highlighted in is different color. Okay. The different regions and corresponding wavelengths in the case of electromagnetic spectrum is illustrated in the diagram which I'll show you here. The total range of wavelengths of gamma ray, X-ray, ultraviolet ray, visible region, infrared, microwave, radio wave is commonly referred to as electromagnetic spectrum. So the electromagnetic spectrum ranges from the shorter waves, from gamma rays and X-rays, to longer wavelengths, the microwaves and radio waves. The division of the spectral wavelength is based on the devices which can be used to observe particular types of energy, such as thermal, shortwave, infrared, and microwave energies. So depending upon the application and need and service, we can use the corresponding spectral wavelength. So any matter within a body, temperature greater than 0 degree emits electromagnetic radiation and electromagnetic energy. So therefore it has a spectrum. Further, the different chemical elements have different spectra. They absorb, reflect spectral energy differently. So different elements are combined to form compounds. Each compound has a unique spectrum due to its unique molecular structure. So which lays as a basics for remote sensing in discriminating one matter from the other. So the spectrum of a material is like fingerprint of a human being. You can see like this, right? You can see it. So the different regions. The spectral range, which varies from 0.45 to 0.52 in the diagram, is used in application areas of coastal environmental studies, soil vegetation differentiation, coniferous or deciduous vegetation discrimination. And in the spectral range 0.52 to 0.59, this is used for vegetation vigorous, rock or soil discrimination, turbidity, and bathymetry in shallow waters. 0.62 to 0.68, strong chlorophyll absorption leading to discrimination of plant species can be done in this spectral region. So whereas above 0.77, the delineation of water features, landforms, geomorphic studies can be done. So this electromagnetic spectrum, which ranges from gamma rays to radio waves, are divided into different regions depending upon their application and use. So visible spectrum lies from here to here, measured in micrometers. Next is the color differentiation. If you have red color, if there is any red color indication in your observation, you can see the peak amplitude will be at red. If you see for green color or dark green, any observation is there, you will have peak variation in green color. For yellow, there will be a variation in peak of green and red. For purple, blue and red. For white, all blue, green, red, which are the primary colors, will be in peak. If it is dark gray, everything will be in a nominal. You can see from this diagram. So next is types of remote sensing with respect to wavelength. Okay, before going to this, I'll show you the same again. If you have any queries in this spectrum, electromagnetic spectrum, you can type in chat box. Any queries in this electromagnetic spectrum region? If no queries, I'll proceed further to the types of remote sensing with respect to wavelength. So, which wavelength you are choosing for which type of remote sensing is that? For reflective infrared remote sensing, the visible spectrum is being used. For thermal infrared remote sensing, the IR is being used. For microwave remote sensing, the wavelength in microwaves is being used. So I divide the table into three. You can see that three: visible, reflective, infrared remote sensing is the first column. Second column, thermal, infrared remote sensing. Third one is microwave remote sensing. So how visible reflective infrared remote sensing is being done. We have sun's energy, so it falls on the object. Okay, falls on the object that we want to measure. So it is reflected. The sun's energy is being reflected. Okay, so it's being sensed by a sensor. So the sensor could be a camera. You can see at the bottom, camera, a photo detector, or a microwave sensor. So camera will be having this wavelength 0.3 micrometer to 0.9 micrometer of diameter. Photo detector from 0.3 to 14. Microwave sensor from 1 millimeter to 30 centimeter. So the electromagnetic spectrum being utilized is visible light. Yeah, you can see the visible spectrum. So the spectral radiance will be, reflected radiance will be 0.5 micrometers. Okay, so the object is being identified by reflectance principle. Reflectance principle. And the radiation source, as we had seen in the first, you can see that, you can see. So this, here the energy source or the illumination is sun in the case of visible reflective infrared remote sensing type. If you choose this type of remote sensing, sun will act as your radiation source. So sun, it falls on the object, then it is being sensed by sensor in this measurements. Similarly, when we see thermal infrared remote sensing, so this is the radiation source is always an object. So where the object is being determined by thermal radiation, measuring temperature and emissivity. Emission comes into play here. So the emission of the photons or emission of energy or radiation is being measured in at an emitted radiance of 10 micrometer, which is B, object B is measured. Okay, so which uses the electromagnetic spectrum in the range of thermal IR, thermal infrared ray is being used at a photo detector is being used there. Okay, photo detector is used for sensing. So then we have the microwave remote sensing. So the microwave remote sensing uses two subsequents. One is the radar principle, which uses back scattering coefficient. Another one is microwave radiation. Okay, microwave radiation or the microwaves are being posed from the object to the sensor, or in turn the radar principle is being used in the radiation source for backscattering coefficient. With that we can find the exact geographical location or the exact information of acquiring the data about it. So using microwaves. Okay, microwave remote sensing, and the sensor used is your microwave sensor operating at microwaves, and we don't have any specific spectral radiance for this, because here we used reflected radiance, here we used emitted radiance. Here we don't have any spectral radiance, as we are doing it with radiation, microwave radiation and backscattering coefficient. With respect to the wavelength being used. Next topic is laws of radiation. Laws of radiation. So how did this laws of radiation came into existence? In the Library of Congress, the Kirchhoff's law of thermal radiation during 1860 stated that at thermal equilibrium, the emissive of a body or a surface is equal to its absorptivity. At thermal equilibrium, the emission of a body or a surface is equal to its absorbability. So this made a major breakthrough in determining the laws of radiation. So which introduced a concept called black body radiation concept. So what is this black body radiation concept is that a black body is an object that absorbs all the light that falls on it. That is, no light is reflected or transmitted. So the object appears black when it is relatively cold. So this is called as black body radiation concept. Okay. The black body radiation concept is that it is an object that absorbs all the light that falls on it, meaning that it will never reflect or never transmit any light that falls on it. Okay. So when it is very cold, it appears black in color. So this is called as black body radiation. So let us see that. So we have a body T1. So a perfect radiator is the one that radiates the maximum number of photons in a unit time from a unit area in a specified spectral interval into a hemisphere that any body at thermodynamic equilibrium at the same temperature can radiate. Is a perfect radiator. Okay, a perfect radiator is that if I have a body, if there is an object T1, so T1 is present, some energy is falling on T1, and that T1, which is a object, emits everything whatever it gets. Okay, E absorbed is equal to E emitted. If that is the case, it is called as a perfect radiator. Okay, perfect radiator is the one which radiates the maximum number of photons in a unit time from a unit area in a specified spectral interval. For example, I have an object. I have an object where it acquires 100 watts of power. 100 watts of power is falling on the object and it emits 100 watts of power. So then it is called as a perfect radiator. And we have another object where 100 watts of power is given to that object and 0 watts of power is emitted. So that we call it as a black body. Meaning is that whatever is sent onto that object is being neither reflected nor transmitted. It absorbs everything, whatever it falls. So that we call it as a black body object. Let us see that also. So which is black body radiation. So the black body radiation field is characterized as isotropic and non-polarized. Isotropic and non-polarized. So it is independent of shape of the cavity. Yeah, black body field radiation is characterized by isotropic and non-polarized structure, independent of shape of cavity. It depends on only temperature. In a perfect black body emissivity, it is equal to unit T due to thermodynamic equilibrium. So these are the characteristics of a perfect black body. So this Kirchhoff's law in thermal radiation, you can see it is being measured with the spectral emissivity to wavelength. So we are taking three bodies. One is a black body, another one a gray body, another one a selective radiator. Okay, since no real body is perfectly emitter, it is not perfect emitter. Its emittance is less than that of a black body. So consider that the black body is emitting at emittance of MB. Okay. Since no real body is perfect emitter, its emittance is less than that of a black body, MB. So thus the emissivity of a real or a gray is denoted as mg, and the body is defined by mg by mb. Okay, let us see that a wavelength versus the spectral emissivity. So a black body will have emissivity as 1, a white body will have 0, and a gray body will be less than 1, and a selective radiator, whatever might be, will be less than 1 always. You can see if any body which is taken as selective radiator will have these characteristics depending upon its wavelength. Okay, it will go in some parts, it will have the condition of black body, in some place it will have the condition of gray body, and some parts it will, in some wavelengths it will have the characteristics of selective radiator. The black body will have emissivity as 1, white body will have emissivity as 0, gray body will be having less than 1, and selective radiator depending upon the wavelength will be less than 1. So that wavelength in terms of spectral radiant flux is being drawn. So the structure of black body, wavelength, selective radiator, and gray body is being drawn according to the Kirchhoff's law. So with respect to wavelength, it is being drawn here. As the temperature increases, the peak wavelength emitted by the black body decreases. As the temperature increases, the peak wavelength emitted, you can see in the graph, you can see temperature is increasing, 2000 Kelvin, 1750 Kelvin, 1500 Kelvin, 1250 Kelvin. As the temperature increases, the peak wavelength emitted by the black body decreases. Okay. As temperature increases, the total energy emitted increases because the total area under the curve increases. So the curve gets infinite close to the x-axis but never touches it. Okay, it will go to infinite. So this is the peak wavelength measured in dotted red. The violet indicates intensity curve for each temperature measurement for different power radiated at each wavelength. Okay, in the infrared region. So from here, this region to this region, it is your ultraviolet. Here is the visible, and here is the infrared. So depending upon the need and necessary, depending upon the application, you use any of this system for measuring its emissivity. So accordingly, we will design it. Next is the Planck's curves, spectral radiant existence versus the wavelength. So where m lambda is the spectral radiant existence measured in Weber per meter square per micrometer. Lambda is the wavelength measured in micrometers. T, temperature of the environment or temperature of the object measured in kelvins. C1 is a constant, C2 is a constant with values 3.74151 to 10 power 8 Weber per meter square micrometer power 4. C2 is a constant 1.43879 to 10 power 4 micrometer Kelvin. So depending upon the wavelength starts from 0.1 ranges to 1000 at different temperatures. How is the spectral radiant existence? You can see that here at 200 Kelvin, at wavelength of 10 it is like this, at 300 Kelvin, at 500 Kelvin, at 1000 Kelvin, 2000 Kelvin, 3000, 4000, 6000. These are these are being defined by the Planck's law of radiation by using the Planck's curves. So what are this Planck's radiation law? Planck's constant or the Planck's radiation. So assume a cavity in a material which is maintained at a constant temperature T. Some object is taken or some material is taken and it is maintained at a constant temperature T. And the emission of radiation from the cavity walls. Okay, we have wall structures surrounding the body. So that emission of the radiation from the cavity walls is in equilibrium with the radiation that is absorbed by the walls. Okay, we say at equilibrium condition they are equal. So then the radiation field in an empty volume in thermal equilibrium with a container at T can be viewed as a superimposition of standing harmonic waves. Radiation field inside this empty material or the cavity at thermal equilibrium or at a temperature can be seen as a superimposition of standing harmonic waves. So this we call as black body cavity schematic, okay, which was given by Planck in the year 19,000. Which was an act of despair because a theoretical interpretation had to be found at any price, no matter how high that might be, was Planck's constant. So here you can see two pictures. One is Planck, another one is Wilhelm Wien. So who is that Wilhelm Wien and what he had done, we'll see. Okay. Wilhelm Wien had given a Wien's displacement law for black body radiations. So let us see the Planck's radiation law. So the Planck's radiation law can be written in dependence on frequency or wavelength, where L is the spectral radiance, lambda is the wavelength, T is the temperature, H is the Planck's constant, C is velocity of light or speed of light, K is Boltzmann constant, nu is frequency, C is equal to lambda into nu. So spectral radiance of a particular temperature with respect to wavelength is given as 2h c squared divided by lambda power 5 into 1 divided by e power hc divided by lambda kt minus 1. So in short, we can write with respect to the spectral energy density as u of lambda comma t, which is L lambda comma t 4 pi by c. So there are two interpretations of Planck's law. One is a surface of a solid body with highest possible emissivity emits exactly the radiation calculated from the Planck's law. A surface of a solid body which will have a highest possible emissivity emits exactly the radiation calculated only from the Planck's law. So this is the first interpretation. So the next interpretation is within a box with walls which have all the same temperature. Within a box with walls which have the same temperature, we get a gas of electromagnetic photons which are in equilibrium with the walls, meaning that in any time interval the walls can absorb and emit an equal amount of photons. So the energy density and the spectral distribution of the photons are described by Planck's radiation. So this is your Planck's radiation law. Which depends upon the emissivity. For a radiating body with emissivity, a spectral radiance or emittance is given by m lambda epsilon 85 h c divided by lambda power 5 1 divided by e power h c divided by lambda kt minus 1. So in short, we can write as it is. So these are the constant values. A black body radiation is the type of electromagnetic radiation within or surrounding a body in thermodynamic equilibrium with its environment. Black body radiation is the type of electromagnetic radiation within or surrounding a body in the thermodynamic equilibrium with its environment or emitted by a black body, which will be an opaque and a non-reflective body with an uniform temperature held at a constant value. So the uniform will be same at a constant value. So therefore the radiation would be having a specific spectrum and intensity that depends only on the temperature of the body. So depending upon the temperature, only we can find the Planck's emissivity. This is an photograph of Planck giving a medal to Einstein. So Einstein, I hereby award you the Planck says, I hereby award you the Planck medal because you expanded my desperate idea of quantum of energy to even more desperate idea of quantum of light. Energy to light. So this was given during a function. Planck to Einstein. So apart from the okay. Apart from the Planck's constant, we need to see about the Stefan Boltzmann law. So if you integrate m lambda or mv over all wavelengths or all frequencies, the total radiant emittance m will obtain for a radiating body of unit area. So that is this m is equal to integration m lambda d lambda or integration mv dv. So you'll get this value, which is Stefan Boltzmann radiation constant. This is sigma emissivity T power 4, temperature is T, measured in Weber per meter square. So where the sigma is the Stefan Boltzmann radiation constant and has a numerical value 5.7 into 10 power minus 8 Weber per meter square K power 4. Okay. So in addition to the Planck's, I had shown another photograph of Willman Vane. This Vane's displacement law. This is what. To obtain the peak spectral radiant emissions, now to obtain the peak spectral radiant emittance, we differentiate this m lambda with respect to lambda with a set equal to 0. And the resultant equation is solved for lambda maximum. So thus we get lambda max is equal to a by t measured in micrometer. So which is Wien's displacement law, or we call it as Wien's constant. So next is the radiance of electromagnetic wave radiation. Always a black body is a hypothetical material that absorbs. A black body is a hypothetical material that absorbs and re-radiates all incident electromagnetic radiation. And the Stephen Boltzmann equation describes the total amount of radiation emitted by a black body as a function of its surface temperature. So which is m is equal to sigma t power 4 sigma is your Stephen Boltzmann constant, T is the temperature. Any queries till this? You can type in chat box. Any queries? If you have, you can type in chat box regarding the thermal radiation laws, or Stephen Boltzmann constant, or the law of radiations. Okay, since there are no queries in the chat box, I move further on to the same topic, which I'm going to repeat it in a different representation, which is again the thermal radiation loss. So a black body is a theoretical construct that absorbs all the radiant energy, striking it, and radiates energy at the maximum possible rate per unit area at each wavelength for any given temperature. Okay, black body is a theoretical construct that absorbs all the radiant energy, whatever falls on it, striking it, and radiates energy at the maximum possible rate per unit area at each wavelength for any given temperature. And no objects in nature are true black bodies. However, we may think of the sun as an approximately having a 6000 degree Kelvin black body, and the Earth is about having 300 degree Kelvin black body. So if we consider, if you point a sensor at a black body, we could be able to record quantitative information about the total information of radiant energy in a specified wavelength, exciting the object and the dominant wavelength of the object. In order to do this, we need to utilize this Stephen Boltzmann law and Wien's displacement law. So Stephen Boltzmann law, which we had seen, and this is your Stephen Boltzmann law. So the Stephen Boltzmann law states that the total spectral radiant existence MB leaving a black body is proportional to fourth power of its temperature. So this is your Stephen Boltzmann law. So you can see in the figure at the top is Joe Stephen, he is Boltzmann, Both together gave the Stephen Boltzmann law. So you can see that the temperature increases, so which is wavelength versus flux density, spectral flux density with the different measurements. So the blue is an 1250 Kelvin measurement, the green is a 1780 measurement, and red is your 2000 Kelvin measurement. So you can see that it is linear increasing. So the total spectral radiant flux existence, total spectral radiant flux existence measured in watts meter square leaving a black body is proportional to fourth power of its temperature. Okay, so the Stephen Boltzmann constant equaling 5.6697 at 10 power minus 8 watt meter square per Kelvin power 4, and T is the temperature in degrees measured in Kelvin. For any queries, if you have, you can type in the chat box. For any queries, type in chat box. That's all with this presentation. So if there are no further queries, we'll have a small IQ test regarding remote sensing. I have 3 questions for you. So whoever knows the answer can put it in chat box. Okay. So I'll present the questions. You can read it out and put the answers in chat box one by one. So you can read the question and in chat box you can type the answer. Okay. So those who are answered BDC, BDC, okay, BDC, BDC, BDC. Most of them are given. So many of them copied the same and given it. Okay, no issues in this. I will just show you the answers also. Kindly await. So those are given your answers can check the presentation for which question what is the answer.
Hello, sir. Hello.